Welcome. Today we're going to be talking about allylic strain and examples of stereocontrol you can leverage from that. So allylic strain comes from the locked chemistry that you get from the four substituents around this double bond shown here. We can leverage this stereochemistry to influence how the reaction will occur at this asterisk position shown here. So the first step of this reaction is simply applying a strong base, deprotonating at this position, and then keto-enol tautomerism gives us this enolate form shown over here. Now this enolate is nucleophilic, and we have a good leaving group over here. So the stereochemistry of the products are going to be influenced by whether or not this bulky leaving group positions itself above or below this enolate. Looking at this position here, we can see we have three different functional groups. We have a small functional group of a hydrogen, we have a butyl group, which we're going to call medium-sized, and then we have the largest functional group, which also contains our leaving group. If we were to just do this reaction experimentally, what we would see is a major product shown here, whereby the enolate has attacked the tosyl group while it was positioned underneath this double bond, and then we have a minor product shown here. And the ratio of major product to minor product is 98:2. So there's a large amount of stereocontrol whereby this tosyl group migrates underneath this enolate and reaction occurs by that pathway. So why should there be that preference? Well, the first thing we need to consider is that there's two intermediates that can give rise to a reaction product. One wherein the large functional group, including the leaving group, is oriented downwards, and the opposite, whereby that same functional group is oriented upwards. It's worth noting that while in the enolate form that is primed to react, this stereochemistry here is locked. However, these three functional groups can rotate, meaning they can adopt whatever conformation is lowest in energy. Now we know, this being the major reaction product, that the largest functional group must want to be oriented downwards. And the reason for that is, if we look at steric considerations, in the top transition state, the smallest functional group, which will have the least steric clashing with the enolate region, is orientated towards the lithium oxide and the methyl oxide here. Whereas if we look at the minor product, so the disfavored transition state, in this form, the butyl group is oriented to clash with these functional groups shown over here. So this allylic strain comes down to what is the optimal orientation of the small, the medium, and the large functional group to minimize these steric clashes shown here. So the top transition state, with this hydrogen aligned towards the enolate groups, this places the reactive tosylate group underneath the enolate, which gives us our major reaction product. The minor product is disfavored because this butyl group will be sterically clashing with the enolate group behind it. And this is the only way that our tosylate can sit above the enolate to react in this way here. So what species typically undergo this allylic strain? Well, it's commonly seen for functional groups containing carbons and nitrogens, shown here, with three functional groups attached to the enolate interacting with a large and a small functional group. And minimizing steric clashes is typically what gives you the stereocontrol for the reaction. Good example of this would be the ENOC reaction, which is an intramolecular nitrile oxide cycloaddition. Starting here, we react it to get this intermediate, which then undergoes a cyclization to give a single isomer shown here. The important thing you really need to be able to do is you really need to be able to draw these perspective diagrams like the one shown here, or these ones from the previous example. Again, stereocontrol is applied at this position. We can see we have three functional groups: a small, in this case a hydrogen, a medium, in this case a methyl group, and a large functional group, which is our reactive functional group in the cyclization. The most important thing is being able to translate a chemical structure like this one into a perspective structure like this one, and provided we don't mix up the arrangement of the functional groups, we should be able to rotate the functional groups such that the smallest functional group is aligned to the functional groups in the enolate group shown up here. I've color-coded the reaction to hopefully make it a little bit easier to follow, but we can see that orienting the large functional group down is required to put the smallest functional group in alignment with the enolate group. So effectively, if we then draw out our transition state based on the idea of this large functional group being orientated downwards, we can effectively map out the positions of, or the stereochemistry of, the various functional groups in the product. Ultimately, that's the most challenging thing, ensuring that you can predict the stereochemistry more so than how the product is actually going to react. You can always look that up. So what happens if we swap the position of the methyl group? Well, if we do that, really there's no difference at all. We still want to orient the smallest of the 3 functional groups towards the enolate, like so. Even though it's a hydrogen aligned to a hydrogen in this case, there's still enough stereocontrol to give you a single isomer from the reaction. So if we look at the stereochemistry here, swapping the methyl group simply changes the stereochemistry on that single position, but otherwise the reaction does not change. In this example, we can see the influence of allylic strain on the alkylation of cyclic enolates. It's the same idea as what we discussed previously, but now we're applying it to an intermolecular reaction. Looking at the reaction itself, here is our enolate. It reacts with this iodoacetate species, and at the end what we see is only a single isomer. And looking at our reagents, we can note that there is a sterically bulky phenyl group and a similarly bulky ethyl acetate group over here. And it's the interaction of these 2 sterically bulky groups that limits the product to only a single isomer. To see why that is, we can redraw our starting material in this projection mode, whereby we're looking down this bond here. When we look down that bond, we can see that our phenyl group is going to be angled upwards, and our cyclopentane group will block this approach to the enolate. That gives us this transition state here, and when we're considering the easiest approach for our iodoacetate, it's going to come up from underneath, forming this new bond shown here and giving us our product. Now what's interesting is when we reverse the functional groups, meaning we replace this methyl group with ethyl acetate and we react it with methyl iodide, what we see is multiple isomers obtained. This highlights the need for having a bulky functional group on either reagent to ensure a single isomer, rather than limiting the bulky functional groups to a single reactant. Next example to look at is olefin hydroboration. This is typically an addition reaction between an alkene, shown here, and a borane, shown here. This typically produces an anti-Markovnikov product, and usually you follow this reaction up with an oxidation step to convert the borane into an alcohol. There are stereoselective borane addition reactions that are possible as per the previous examples. So if we take a look, here is our olefin. It has locked stereochemistry shown here in the dashed box. We have 3 functional groups that can rotate and spin. One is small, one is medium, one is large. If we add our borane and then oxidize it, what we get is this major product here with this stereochemistry shown. For this to occur, what we need is this transition state to form preferentially. What we have is a borane with 2 R groups positioned over the alkene like so, and then we have our 3 functional groups arrayed in this way, with the small and medium oriented towards the borane and the largest functional group oriented away from the borane. These 2 functional groups at the terminus of the olefin, these are less important. So if we swap those around, it doesn't really matter so much. We still get the same stereochemistry occurring. What's important are these 3 functional groups, 1 carbon removed from the olefin. Now, one thing you might be wondering is why would it have this staggered conformation like shown here? Well, one reason is sterics, particularly if you have larger functional groups along this carbon chain. You'll see a conformation whereby these steric clashes are minimized. However, the second reason is a stereoelectronic reason. So it's to maximize orbital overlap, which is what you see in a staggered conformation. So if we take a look at this carbon to carbon sigma bond between the blue and the pink carbons, if we were to draw the anti-bonding orbitals of that sigma bond, we're going to generate an orbital out here. This is going to overlap with the sigma bond orbital between the green carbon and the red carbon positioned behind it. I like to think about this in the same way that I think about resonance structures, in that even though this isn't a particularly likely situation to occur, it does show a way that electrons can be delocalized. And any of these overlapping orbitals, while electrons are being delocalized, are going to have a stabilizing effect over the entire molecule. So this staggered conformation is good for stabilizing atomic orbitals when they are delocalized. We can look at that for staggered olefins now. So here is a simple olefin in the staggered conformation like I've shown. We have 2 pi bonding orbitals shown here. If we draw out the pi anti-bonding orbitals, we can see that these 2 orbitals are potentially going to overlap with the sigma bonding orbitals behind them in the staggered conformation. So again, this delocalization that can occur, stabilizing the pi anti-bonding orbital, is a factor whereby olefins will adopt this staggered conformation, especially when you consider that the pi anti-bonding orbital actually will repel, adopting this shape more so than this shape. So really, these orbitals should be repelling and really overlapping the sigma orbitals behind them. Now back to our olefin hydroboration. If this is our starting material, we can draw out a transition state like so. We know it's anti-Markovnikov, which means that the hydrogen is going to be positioned over this one, boron over this one. We can draw out our 3 functional groups, smallest and medium pointed up towards the borane, the largest functional group pointed downwards, away from the borane. This is going to lock in the stereochemistry like so, and if we oxidize this borane, we're going to get the alcohol shown in this position here. Amides. We should be familiar with amides, as well as with the resonance forms that they can adopt. If there are larger R groups attached to those amides, that can impart some diastereoselectivity over the conformers that you see. Because certain conformers are biased, if we were to react those amides, that bias will be carried through into the products of those reactions. So here we have an amide shown here. It has some large functional groups attached to it. We have a reaction whereby a nucleophile attacks an alkene. It then reacts to kick out this leaving group, giving us a product with some stereocontrol. Now, why would that be? So, first thing we need to do is we need to draw out the zwitterionic form of the amide. So effectively this form shown here. And once we do that, we have our negatively charged oxygen, and then we have our 3 functional groups shown here. We have a small, a medium, which contains our alkane, and our large functional group, which is an aromatic ring. There are 2 possible conformers we can draw, one whereby our reactive alkene is oriented downwards, and the second conformer where we have the reactive alkene oriented upwards. These are the only 2 conformations whereby the alkene will be in the correct position to react and kick off this leaving group in the background. Now, if we spin our functional groups around, to orient the alkene downwards, this creates a clash between our aromatic ring and our oxygen anion. So this isn't liable to form. If we keep rotating the functional groups, we can eventually get the hydrogen position neighbouring to the oxygen anion, and this is going to minimise steric clashing. So effectively, we need this medium functional group pointed upwards above the leaving group, imparting this stereocontrol we can see in the final product. Much like amides, diketone enolates will react in a similar fashion. So effectively, we take our beta-diketonate, we add a base which deprotonates it. We can then introduce this phenylmethyl bromide, which we can really just consider as an electropositive target for a nucleophile, shown here. Now, I haven't drawn in the box, but we can see that this is our region here of locked stereochemistry, and we need to draw out our projection over here to see which side is more sterically congested, or which side is more accessible to our electrophile. Doing so, we can see that the influence of this benzyl group is going to be covering the top half of the intermediate shown here, and we also have a lithium metal ion in the vicinity. And it's also worth noting that metals typically have ligands collating to them, so things like coordinating solvents. So while it doesn't look large, there's potentially large functional groups attached to that lithium as well. So sterically, one half of the transition state is effectively blocked, and the lower half, drawn like this, is open for nucleophilic attack on this electrophile down here. So if we look at the ratio of the products, we have 100:1 for addition of our reagent on the opposite side of this benzyl group. However, you might expect that once you've created this diastereomer in the previous reaction, that considering it's under basic conditions, all that would need to happen is you would need to deprotonate here, and then you would get epimerization occurring. So any stereocontrol that you introduce into the reaction is going to be lost simply because you deprotonate, and that's going to racemize this carbon here. However, this doesn't actually happen, and it comes back to allylic strain once more. Effectively, if we create a molecule like this one, if we are going to deprotonate it here, what's going to form is we are going to lock these functional groups such that they're sterically clashing with one another. It doesn't matter which way that we draw the molecule, there's always going to be a steric clash occurring if you deprotonate. So effectively what this means is you don't see epimerization because deprotonation would create too much strain in the products. So to summarize, allylic strain can be a powerful tool for directing stereoselectivity. It's relevant for reactions involving enolates, amides, olefin hydroboration, as well as the Enoch reaction. Probably the most important thing to be able to do is to be able to draw these chemical projection diagrams, because it's only by visualizing the transition states that you can understand where the stereochemistry will be retained. So unless you're really good at visualizing things in 3 dimensions in your head, consider a chemical modeling kit or some sort of computer program to assist you with visualizing these transition states. That's all for today. Thanks for watching.